Okay, so one of the main reasons why we want to know where a force is, where is the centroid or the first moment of area for a system is because sometimes we have distributed forces, right? So we're gonna talk about a new concept here, which we're gonna call distributed forces. In distributed forces, we can conceptualize a system where, say, we have a car on a beam. In that case, the car has continuous forces pressing on the beam. But in order to analyze the system, we would like to make it simple, where we say, okay, let's map all that mapping is a mathematical construct where we're gonna map that whole distributed force to a single force, the same magnitude, and placed at a location where it would cause the same momentum and the same effects. So in this case, picture this is I don't know, a truck or a car, and the maximum load or the distributed load can be applied to this point P. So starting by the left-hand side, if we assume that we have a distributed load, dW for weight or force because of a weight, let's say, but is going to be also the same, just a coincidence, that the force is going to be the same as the area, like one by 1 cube is 1 kilogram or 1 Newton, something like that. It's just a coincidence that the weight is the same as the area for simplicity. So let's picture a force differential of W applied at a point in X, which is our horizontal axis, where this whole distributed weight or area can be applied or simplified to a single vector. So the mathematical function that we use, of course, because that's why we're doing the simplification for area, is integral. And we say from point O, which is going to be the same as coordinate 0, to the length, whatever this is, 10 meters, 100 meters, so from 0 to the length of that beam or that system, we want to compute the differential of the function W, and the function W is as a function of x, right? It's varying with respect to x, as with respect to x. So the function W with respect to x from 0 to L. Of course, the function W could be pretty complicated, but we'll see methods of simplifying that as well. Maybe we can simplify that as a rectangular shape plus a square and another rectangular shape. We'll see that. We'll see how to do that unless they already give us the function. We'll have to simplify it somehow. But we already saw how to compute the centroid of a 2D body. So we're going to apply that concept here. Again, the concept is that from a distributed load or distributed force, we're going to find a point force at a point P where the whole distributed load can be characterized as a single force at a point that we have to find, and this is the centroid. Okay, later on that centroid would help us to compute moments and other stuff. So that's the concept right here. Now let's look at an example to understand what we mean. So in this case, we have an example where they give us a distributed load of 15 newtons per meter. Notice that is divided by meter because if you were to create a little table right here of length, say at 2, at 4, at 6, and this is meters. And the actual force in newtons, you cannot find that very easily. You can say that at 2, well, it's not as easy as I wanted it because we have to find the slope right here. So let's say at 6. At 6, this force is 6 meters times 4,500 newtons per meter. Okay, so this answer is going to give us meters, but the solution is 6 times 45, which we can go to 6 times 45 is 270. So this force right here is 270 newtons. At 2, we'll just have to find what's the force here, and that slope we can find by 45 divided by, so this is triangular shape, and actually we can do that right now. So let's go ahead and build this table in a minute, but first do this by centroid and finding this distributed load by the method that we learned. So we have two options here. One option is to divide the force into, so option 1, we divide the force into square, or not a square, but a rectangular shape, where this is 6 meters, and then a triangular shape where, so the square is going to have a uniform force of 1,500 newtons per meter. That's 1,500 newtons per meter. That's distributed around this beam. And then here's only 1,500, obviously, which is what I was going to do with the table. But here is going to be 4,500 minus 1,500. So here it's going to be 3,000 newtons per meter. And then we find the distributed forces by doing this plus doing the rectangular shape. So at any point, the force is equal to the force at the rectangular shape as a function of L, or length, plus a force in this triangular shape as a function of length. Another method is, which is probably simpler, so we don't have to subtract anything, is to create a beam again. Okay, here the beam is right here. And in that method, we're gonna say, well, let's just do two triangular shapes. One shape is going to be this one from 1,500, and the other shape is going to be that one up to 4,500 newtons per meter. So that case is pretty simple because it's just two triangular shapes, and it's the same thing where force is equal to force triangular shape 1 plus force over the triangular shape 2 as a function of L. But the distances are the same. Here we have to change the 3,000, but both ways will take us to the same result. So let's carry on with this one, which is what the example says. And if you want, you can do this one, the second method, which is easier computing the areas, but you have to be careful that it's not 45 anymore, it's 3,000. It's not 4,500, it's 3,000. So here, triangular shape 1, we have a table, triangular 1 and triangular shape 2, where you're going to have a table where we're going to compute the area, the centroid in x, and x times area. And that is for triangle 1 and triangle 2. So triangular shape 1 and triangular shape 2. Okay, so area for triangular shape 1, we can do it here. Area is equal to, we know that the area of a triangle is 1/2 of the base times the height. So b times h. Area is equal to 1/2 of the base, which is 6 meters, times the height, which is 1500. Let's move it over here. Let's do it again. Area equals 1/2 of base, which is 6 meters, times height, which is 1500 Newton meters. All right, that will give us an area of not meters, but that region. That's why here we said at the beginning that we can assume that the area could be this force. Here, that area is going to give us a unit of force. So it's the distributed load of that whole triangular shape. All right, and why 6? 6 is this dimension right here, the base of the triangular shape, and 1500 is because of this height. So for triangular 1, we have 6 times 1500. 1500, which is 9,600 divided by 2, 4,800. All right, so 1500 times 6 divided by 2. I don't know why I didn't say 1500. I said 1600. Okay, 6 times 1500 divided by 2 is 4500. So this area right here is 4500. Yeah, and that area is actually a distributed load as a force, distributed force. So this whole triangular shape is applying a force on the beam of 4500 newtons. Okay, since I'm going to give you the file here, I'm going to rewrite this so you can understand what I'm saying. Okay, so that region, if you don't want to think of area, think of a region. That region is having a distributed load of 1500. It's having a distributed load of 4500 newtons. Let's do area 2, now that we're doing this column. Area 2 is equal to 1/2 of base, which is the same, times height is 4500. All right, so I'll go here, it's 4500, 13,500. All right, perfect. Okay, so we know how to do the centroid of a triangle. The centroid of triangle 1 is equal to 1/2 of the height. So 1/2 of 6. Which is equal to, sorry, 1/2 of 6, not 1/3 on 6. The area is 1/2 of base times height. The centroid is 1/3 of the length. So this is equal to 2, and this is units of meters, which is this value right here. So 1/3 of 6, and for a triangular shape, that is something that either we look at the table that we had before, or we just simply memorize that is 1/3 of the length. Okay, so this is 2 meters, and the centroid for triangle 2 is also 1/3 of, what is this? 1/3 of 6, except for we're starting from this end. So is 1 minus 1/3 of 6, right? Because, sorry, 6, not 1, 6, because the base is actually on this side. So we have to locate this distance right here. And that is, we know that 1/3 of 6 is from that centroid to the base of the triangular shape. So what this is let's get to this point and then subtract that. So this is 6 minus, because we're going to go back, 1/3 of 6. 1/3 of 6 is 2, so this is equal to 4 meters, right? Because the origin is right here. Or, this is not on the table, but you can remember that the centroid from the tip of the triangle is 2/3 of the length, right? So if we do 2/3 of 6, hold on a second, this is 6 times 2, 12 divided by 3, 4. Yeah, so this distance here is 2/3 of L. So whichever is simpler for you. If you do from the base, but you need to go back, you do the whole length minus the 1/3, or simply remember that in a triangular shape, and it doesn't have to be a rectangular shape, it's just any triangular shape, because the area will balance out the height, is base, height. The centroid is 1/3 of the base, in this case the height, right, because we're going up from the base, or from the top is 2/3 of the height. This point can be computed from both ends. All right, so 2/3 of 6, we just said 2 times 6 is 12 divided by 3, 4. So we put here 4 meters. All right, so what we have to do now is do 4,500 times 2, which we have up here. 4,500 times 2 is 9,000, and that is newtons per meter, and this is 1350 times 2. No, 13,500 times 2, 27. 1, 2, 3 newtons per meter. Okay, so now we can have the, oh man, hold on a second, what did I do? Times 4. It's times x, right? 54,000. It's not times 2, it's times the centroid. The centroid is 4. So 54,000. All right. So let's go ahead and move this a little because we don't have enough room here. And we have to do summation here. So first of all, let's check that we have the same results as they do. Yeah, 9,054 because they have kilonewtons per meter. But yeah. So as we did before, the next step is to do the summation of the centroids because it's 2 regions to compute the actual centroid of the single region. So this is 54 and 9, well, this is 63,000 newtons per meter. Okay, so that is the total force of this region. So at this point, we can actually go back and create the table that I wanted to do at the beginning. So if we want to find at 6 meters, we can do something else here. If we do 63,000 divided by 6, 1, 2, 3 divided by 6, 63,000 divided by 6. So this force right here is whatever I got, 10,500. So at that point, if you were to put a force sensor, that point you get a force, a local force of 10,500 newtons. At 4, and why divide it? Because here we have Newton meters, so we have to divide by meters just to have the Newton unit that we care about. 63 divided by 4 is 15,570, right? 15,570 newtons. And at 2 is 31,500. Okay, so those are local forces. But if you want to have the whole force, what you need to do is what we just did, the region of the first area and the second area combined, which is right here. Okay, so now that we have that, we can actually compute the center and the total force. All right, so the total force is, actually is right here. So we have the area, summation of area is 13,500 plus 4,500. So let's do that. 4,500 and plus 13. It's 18,000 newtons. 18,000 newtons. Summation of area is 18,000 newtons. Okay. All right, so if we divide, this is also from last video, if we divide 63,000 divided by 8,000, or 18,000, sorry, 63,000 divided by 18,000, we have 3.63, yeah, it's 3.5 meters, right? Yeah, we have 3.5 meters. So that force is, first of all, is the summation. The total force is the summation of both regions. Okay, so one thing is, what if you were to measure the force at that point, the real force, is what we did before, is the force at that point divided by the length. Another different, so that's of course a 2, 2.5, 3 at any continuous measurement. That's what you get. And you can put sensors and add the forces and get it. Or you can mathematically find it by what we did. Find the region 1, the region 2, and add them together. This part right here. Add the areas or the regions. I don't want you to get confused. This area is not in units of length. It's not meters squared. These areas or regions are in units of newtons. And we just saw why, because the unit of the force given is kilonewtons per meter. And so if you multiply meters times kilonewtons per meter, you're going to get it kilonewtons or thousands of newtons. All right, so the total force is 63,000 newtons per meter divided by 18,000, and we get units of meters. But the total force is this total amount of force on the region. Therefore, this is 18,000. located at point P, and point P is the centroid. All right, so with that info, they tell us now determine the equilibrium forces. And we know how to do that. We know that summation forces in X equals 0 to have perfect equilibrium. Summation of forces in Y equals 0, meaning that maybe they had no force before, and they put a car on top and waited until the system stabilized, waited for a few minutes or whatever they needed to wait for a day. No more vibrations were there. The system was completely static, and at that point, they compute the forces. That's what it means, static equilibrium with forces applied. So when we go and capture the equations, we're going to see that, please remember, we saw that before, that this point right here is going to have force in X and force in Y. We have a force here that's negative 18,000 at 3.5. And this is a roller, hence it's only one force. So, and of course we're gonna have, are they asking for a particular point? Yeah, at A, right? Actually, they're doing at both points because the question is determine the support reactions. So BY and AY. But notice that we have no more forces in X because this one here is completely static. Therefore, dx is equal to 0. There's only one force, and that is equal to 0. But in y, we have more than one. In y, we have ay plus by minus ay, sorry, not ay, what is this called? 18,000, or the distributed force, or W, whatever you want to call it, FW, equal to 0. And this happens to be ay plus by. Remember, the coordinate system is x positive to the right, y positive vertically up, so this is negative, but on the other side of the equal sign, we get a positive, and that's what we're going to do here, equal to 18,000. Perfect. So we have two unknowns, but only one equation. So let's go ahead and compute another equation. So we have two equations, two unknowns. So at A, ay is going to be 0 because it's on the point, equal to 0, and counterclockwise is positive, remember. So whatever force is going to be counterclockwise, that's going to be positive. So 18 kilonewtons is negative, so negative 18 newtons times 3.5 meters, and by times 6 meters is equal to 0, which is this equation right here. So let's solve for it. 18,000 on the other side times 3.5. We can do that right now. 3.5 times 8,000 is 63,000, which is the total amount of distributed force, actually, if you remember. It's the same thing that we did here. We're doing 3.5 times 18,000. So the total amount of distributed force is equal to by divided by 6. And this is in meters, this is in Newton meters. Newton meters, but meters on the denominator, just only going to have newtons. 63 divided by 6 is 5,000. All right, so by, what do we get here? 10,500 newtons. Okay, so that is question A. If they also ask you, well, but actually I also want to know AY, so we know how much support we have to build, or what type of steel, or whatever, what density, what amount of force are we going to be able to see. It's pretty simple. It's just solving for AY. So let's do summation of moments at A, and then remember, counterclockwise is positive, so this is equal to 0. And at A, oh wait, what are we doing? That's the one we just did. I apologize. At A, we find B, so now we have to do moment around B. Condition is that we are saying that counterclockwise is positive. So at B, Bx and By are 0. 18,000 is going to be positive times the length, which is 6 minus 3.5. Okay, so 2.5, right? And this is counterclockwise. AY is clockwise, so negative, times 6 is equal to 0. All right, negative AY times 6. Yes, perfect. All right, so now we just have to solve for this guy, which is AY is equal to 18,000 times 6 minus 3.5 is 2.5. And this is newtons, this is meters, divided by 6 meters. This is equal to, the answer is going to be in newtons. So 18,000 times 2.5, or if you want to put the whole thing down here, is 6 minus 3.5 divided by 6, 7,500. All right, so that's the value of AY.